Hi students, good morning all. Our today's point is fourth point in the vehicle on the banked road. And the vehicle on the banked road is the third point in the applications. And so write down part first is from the circular motion in which fourth point is applications, and in the applications third point is vehicle on the bank road, in which fourth point is our today's main point, speed limits. So write down speed limits. Speed limits. And the question will be asked on this point is a very important question, and so write down this question and mark it as VVIMP. And the question is derive expressions for lower speed limit and upper speed limit for the vehicle on the banked road. So write down this question. Derive, derive, derive expressions for a lower speed limit, lower speed limit, and B upper speed limit, upper speed limit for a vehicle on the banked road. For 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 vehicle on banked road. This is our question on this point. We know that the answer of this question is expressed in 4 points. First point is consideration, second is diagram, third is notation, and fourth is the main part, and it is the mathematical expression. So write down the first point of this answer. First point. Consider the vehicle. Consider the vehicle is taking. Consider a vehicle is taking a turn a turn on the curved road, on the curved road, which is banked, which is banked. This is our consideration. Write down this consideration. And the second point of this answer is the diagram, and it is for two parts. First is for lower limit. So draw the diagram for the lower limit first. This is our vehicle. This is the center of gravity in which the weight is vertically downward. Show this weight vertically downward. The normal reaction is perpendicular to the road surface, and it makes some angle with the vertical. If you show the normal reaction perpendicular to the road surface, then Please complete this parallelogram first. This is a normal reaction. This is n cos theta. This is n sin theta. This is angle of banking, and this is towards the center of motion. This direction is towards the center of motion. Center of motion. Now here the friction is along the road surface between the tires and road surface. So show this part of here. Draw this diagram. Complete this parallelogram first. Now this is a friction, force of friction, and this is Fs into cos of theta, and this is Fs into sine of theta, and this diagram is for figure A, and it is for lower speed limit. Then draw the next diagram, and it is for the upper speed limit. Show this diagram one after another or one below the other. So this diagram is for upper speed limit. Upper speed limit. Vehicle is same. This is mg. Complete this parallelogram. This is n into cos of theta. This is n shaded by continuous line, and in this case the force of friction is along the road surface and the point of contact with the tires. In previous case, Fs sin theta is vertically upward, but in this case Fs sin theta, Fs sin theta is vertically downward, and in both cases Fs cos theta is a horizontal component. Draw these two figures, and this is the direction to the center of motion, to the center of motion. Draw these two figures, and the third point is the notation. Write down the notation. Let m mass of the vehicle r radius of curve, theta angle of banking, g acceleration due to gravity, and normal reaction, perpendicular to road surface. Write down this also. Normal reaction perpendicular to road surface. Fs, force of friction. And the point 3 is about the notations. Write down these notations properly. And the fourth point is the mathematical expression, in which we consider 2 points. First part is for the lower speed limit and second part is for upper speed limit. So write down fourth point for mathematical expression, in which we shall consider 2 points. First is lower speed limit. In order to derive the expression for the lower speed limit, we are going to use the diagram in which we consider different components. Let us see this diagram, in which the normal reaction and force of friction are splits up into rectangular components. So right here, let us split normal reaction. Capital N and force of friction Fs into rectangular components, as shown in figure A. See this figure, in which consider only horizontal components. The horizontal components are oppositely directed, n sin theta and Fs cos theta, and they both provides the required centripetal force. Right here, in which horizontal components provides required centripetal force, provides a required centripetal force, provides a required centripetal force, and from this sentence we are going to form equation first. mv square upon r, mv1 square upon r is the centripetal force, and from figure the horizontal components n sin theta and fs cos of theta are oppositely directed, so the negative sign is given. This is our equation number 1. See the figure in which weight of the vehicle is balanced by the vertical component. So write down, and the weight of vehicle is balanced by, and weight of the vehicle is balanced by vertical components. See the figure in which weight mg is balanced by vertical components, and these components are n cos of theta and fs sin theta. Both are along the same direction, so their sum provides the weight. This is our equation number 2. Now, for the minimum speed or for the lower speed limit, for the minimum speed using fs is equal to mu(s) into n, in above equation, using fs is equal to mu(s) into n, and solving we get, for minimum speed using fs is equal to mu(s) into n, and solving we get v1 minimum is equal to square root of rg in bracket tan of theta minus mu(s) divided by 1 plus mu(s) into tan of theta. Denote it as equation small a. And this is the expression for the lower speed limit. So write down, this is an expression for lower speed limit. This is an expression for lower speed limit. And it is clear that if mu(s) is greater than or equal to tan of theta, then then V minimum is equal to 0. Then V minimum is equal to 0, and it is for the rough road banked at smaller angle. Write down, it is for a rough road. It is for a rough road banked at smaller angle. It is for rough road banked at smaller angle. A rough road banked at smaller angle. Smaller angle. In this way, we completed the mathematical expression for the first part, lower speed limit. The second part of this mathematical expression is for upper speed limit. Upper speed limit. And it is also expressed by using the diagram. So see this diagram, in which the force of friction and the normal reaction are split up into rectangular components. So right here, let us split normal reaction capital N and force of friction Fs and force of friction Fs and force of friction Fs into rectangular components as shown in figure, into rectangular components as shown in figure, B. See this figure. Only difference is the direction of Fs sin theta see the direction of Fs sin theta, or compare the direction of Fs sin theta in figure A and B, in which the horizontal components provides required centripetal force. Required centripetal force. The difference is only the direction. So from this discussion, we make an expression such as mv1 square upon r is equal to n into sine of theta plus Fs into cos of theta. plus Fs into cos of theta. This is our equation number 4. Sorry, this is equation number 3. Let us see the horizontal components n sin theta and Fs cos of theta in figure B. And the weight and the weight is balanced by vertical components, and the weight is balanced by the vertical components. See the vertical components in the figure B, and it shows that is equal to n into cos of theta minus Fs into sin of theta. This is our equation number 4. At maximum speed, at maximum speed, using Fs is equal to µs into n, and solving these equations, at maximum speed using Fs is equal to µs into n and solving these equations, we get V1 maximum is equal to square root of Rg in bracket tan of theta plus µs divided by 1 minus µs into tan of theta. Denote it as equation B. This is our main expression of this part, and so write down this is an expression for upper speed limit, and equation A is for lower speed limit or minimum speed limit. Write down the points for note. First point is, if µs is equal to cot of theta, then Vmax is equal to infinity. But µs max is always equal to 1, and therefore at that point theta is greater than or equal to 45 degree, and Vmax is equal to infinity. However, for heavily banked roads, that is theta is greater than or equal to 45 degree, the minimum speed may important. This is our first point. The second point is, if mu(s) is equal to 1, then for both equation A and equation B, the value for the maximum velocity is same, square root of rg into tan of theta. In this way we complete the main point, speed limit. Our next point is a conical pendulum, and it is the fourth application in the main point applications. So write down part first, in which the fourth point is application, and in that application this is a fourth point, conical pendulum. Conical pendulum. Let us see first what is mean by conical pendulum. And so write down the question. What is a conical pendulum? What is a conical pendulum? We are going to understand first what is a conical pendulum. But in order to understand what is meant by conical pendulum, we must know the simple pendulum. This is a simple pendulum. A metal sphere called as a bob attached to the spring from a rigid support, and it is called as a simple pendulum. If the bob is pulled aside and released, it performs oscillations. So it is called as a simple pendulum. But instead of oscillating, if the bob performs UCM, that means uniform circular motion, then see here, it's a string forms a cone at the point of suspension, and this is called a conical pendulum. And this demonstration is helpful in order to understand what is a conical pendulum. So write down the answer. If a bob of a simple pendulum if a bob of a simple pendulum performs UCM instead of oscillations, then its string forms a cone at the point of suspension. This is called a conical pendulum. This is called a conical pendulum. And important question will be asked on this point of conical pendulum is, derive an expression for the period of a conical pendulum. So write down this question. Derive an expression for for the period of conical pendulum. Period of a conical pendulum. This is important question. So denote it as VIMP. And the answer of this question is also expressed in 4 points similar like other derivations. First point is a consideration in which we consider a conical pendulum. So write the consideration as consider a conical pendulum with its point of suspension is capital A, and C is its a mean position. C is its mean position below point of suspension. This is our consideration, and as already stated, the next point is diagram. Draw the diagrams one below other or side by side. Suppose that this is for first and this is for second. This is for inertial frame of reference and this is for non-inertial frame of reference. Let us complete the diagram for the inertial frame of reference first. This is mg, this component is T0 cos of theta, this component is T0 and this component is T0 cos theta and this is T0 sin theta. This is a point of suspension A, B, and this is a center, and this is a height, and it is equal to L into cos of theta. This is a length, and this figure is for inertial frame of reference. Figure A. Inertial frame of reference. After completing the figure for inertial frame of reference, our next figure is for non-inertial frame of reference. Draw the figure A first and then figure B. It is for non-inertial frame. This is a point C. This is T0 into cos of theta. This is T0. This component is T0 sin of theta. This is the angle theta, length L. This is H is equal to L into cos of theta. Only the difference between the two diagrams is shown here. Centrifugal force mR omega square. This is the radius of the circle. In both diagram, draw this part by dotted lines or by continuous lines. Figure B. Non-inertial frame of reference. Draw these two figures side by side or one below the other. Third point of this answer is a notation. Write it. Third point. Let, comma, M mass of the bob, L length of string, R radius of circle, theta angle of position, T0 tension along string, and T is the period of conical pendulum, and H is the distance between AC. This is our notation. And the fourth point is the mathematical expression, and this mathematical expression is expressed by using the figure. So from the figure we know that the tension along the string T0 is splits up. So right here let us split tension T0 into two components, into two rectangular components, into two rectangular components, and from these two components, let us see the figure. The horizontal component provides the centripetal force. So right here, in which the horizontal component provides required centripetal force. And from this sentence we are going to form equation 1. T0 sine of theta is our horizontal component, and it provides the centripetal force, and this centripetal force is expressed in terms of omega, that is angular speed instead of linear speed. And the weight of the bob is balanced by the vertical component, and from this sentence Let us see the figure. T0 cos theta is a vertical component and weight is mg. This is our equation number 2. And therefore, from equation 1 divided by 2, we get omega square is equal to g into sine of theta divided by r into cos of theta. This is our equation number 3. From the triangle, see the figure. From the triangle ABC, sine of theta is equal to r divided by L, and therefore r is equal to L into sine theta. Using this in equation 3, we get therefore omega square is equal to g divided by L into cos of theta, and therefore omega is equal to square root of g divided by L into cos of theta. This is our equation number 4. If period of the conical pendulum is given by 2 pi upon omega, because the bob is in UCM, because bob is in UCM, and therefore from equation 4 we get T is equal to 2 pi upon square root of a g divided by L into cos of theta, and therefore T is equal to 2 pi into square root of L into cos of theta divided by g. This is an expression for the period of a conical pendulum. This is an expression for period of conical pendulum. Now using H instead of L cos theta, the equation of the period becomes H upon G. This is also an expression for the period because H is equal to L into cos of theta. In this way, we derive two expressions for the period. Now, if a frame of reference is attached, now if the frame of reference is attached to the bob and if bob is in UCM, then centrifugal force balances all resultant forces, all real forces, and in this case the magnitude In this case, the magnitude of centrifugal force is same as that of T0 into a sin theta is equal to m r omega square.